Alright, so this is the next video. The last video we talked about separable equations, how to solve them. And I really think it's important that I do example problems. So at the end of each bit, I'm going to pick out some problems to do, and I'm going to try to pick a variety of different problems without making so many that it's like a homework assignment. So last time I suggested, and if you haven't done it yet, you can try these problems on your own first. Problem 1, problem 11, problem 21, problem 33, and problem 34. So those are the problems that I'm going to do right now. I'm going to go through each one, and hopefully it helps. And if you don't mind, please liking the video and subscribing. It'd help out a lot. So yeah, that would be great. And let's go ahead and get started. So number 1 says that dy dx is equal to, or I'm sorry, well yeah, I'll just move it over, sine of x plus y. So I just moved that over. Is this separable? Well, the problem is I can't get these variables in such a way that they're all by themselves, right? So if I multiply over by dx, well, I still have this x plus y that's coupled here. And there's not really anything I could do to fix that. So this differential equation is not separable. So that's pretty similar to examples we did in the last video. I just did a problem to emphasize it. Okay, let's look at problem 11. Problem 11 is x times dv dx equals 1 minus 4v squared over 3v. Maybe v stands for velocity if you want to think of it from a physics perspective. Okay, so is this separable? Well, let's see. I can multiply over by the 3v. I can divide over by the x, and I could also divide over by the 1 minus 4v squared. So I can get 3v over 1 minus 4v squared dv equals 1 over x dx. So now this is separable, and it's separable again because our v's, our dependent variable, is on one side, and our independent variable, our x, is on the other. So if you can write your differential equation like that, you can just use methods of separation of equations, separable equations. So in this case it does, so it's completely fine. And once you do this, the trick is to integrate both sides. Okay. Well, on the right hand side, that's pretty easy. That's just the natural log of the absolute value of x because of the domain, plus, I'm going to call a constant c1, is equal to, I'll factor out the 3. This one's a little trickier. So I integrated the right-hand side, and I just factored out the 3 from the integral. Okay, but this isn't too bad actually, because we can do a u substitution for this guy. So now the goal is to solve this. So this is just a method of integration, 1 minus 4v squared. Hopefully you're good with integration techniques. If not, I'll eventually make a calculus playlist. This is just one that I really wanted to do with DiffyQ because that was one of my favorite classes. So I'm going to do this. dv. Okay, so differentiates both sides, and I solved for this part here is right here. So I can substitute that in. That's the natural log of the absolute value of x. No need for a subscript. Plus c1 equals 3 times the integral of, well, we'll have a minus 1/8 from the du, a u in the denominator, because that's what we're substituting, and then, of course, the du. Sorry about that. Got a text message and had to head somewhere, but I can continue in the parking lot here. Okay, so we have the natural log of x plus some constant equals, and now we're going to go ahead and do this integral. So again, this is going to be, I can factor out the negative 3/8. And again, we're going to get the natural log of u, absolute value, plus a constant called C2. Okay. All right, so we have the natural log of x. I'm going to move over the other log. And I'll also substitute what u is. We said u was 1 minus 4v squared. And we'll set that equal to C3. And we'll say C3 equals, well, just C2 minus C1. Okay, so that's just a collection of constants. Going forward, I'll just keep it C. But I'm doing it this time kind of slowly just so we can see and understand why everything is the way that it is. All right, so using log properties here, I can say this is equal to, plus the natural log of 1 minus 4v squared to the 3/8 power equals C3. So I just take your multiplier out here, and it becomes the exponent inside the log. Hopefully you remember that log property. If not, well, that's what it is. The other log property is that we can rewrite this as the multiplication of the two arguments, since we have the addition of two logs. So these two lines are just log properties. And now I'm going to raise everything to the e power to get rid of the natural log. Okay, and we'll call this C4. And C4 is just e to the power of C3. So you raise everything, you take the exponential of each side, you can get rid of the natural log, of course. Okay? Well, we want to solve for v. So let's divide over by x. So you have C4 divided by x. If you raise everything to the 8/3 power, it's supposed to be a 3. Then we can get 1 minus 4v squared equals C4 over x to the 8/3. Okay. Or 1 minus C5 over x to the 8/3 equals 4v squared. And C5 in this case is just C4 raised to the 8/3. You can kind of see why I would rather just keep it as C. It gets a little tedious, but I do want to show all the steps if possible. Okay. Alrighty, so we have that step. Now we can divide everything by 4. You could factor out a 1/4. Of course. And then if we take the square root of both sides, v is 1/2 the square root of 1 minus C5. Okay. So normally when I go through a problem like this at any point, I would just say C5 is equal to C, and I'll just carry a constant C, even though it's maybe not the best notation. But that's how you do that problem. We have v completely by itself. We've solved that differential equation. Question 21 is somewhat similar, but we're using theta. So, and we have an initial value. That's why I picked that one, is because I also wanted you guys to see an initial value problem. 1 over theta dy d theta equals y sine theta over y squared plus 1. Okay, so we can say dy is equal to y theta, I'll multiply by the theta here, sine of theta over y squared plus 1 d theta. Okay, and we know y evaluated at pi equals 1. That's your initial value. Okay. All right, so we can multiply over by y squared plus 1 and divide over by y. And thankfully, this is separable. We've successfully separated our equations. That's good. That's the only trick we know at this point, so good start. And this is, of course, equal to, if you divide out by the y's over here, that'll just be y plus 1 over y dy equals theta sine theta d theta. Okay. Just get a little drink of water. Okay. So now we integrate both sides. Once you successfully separate, the next step is to integrate both sides. Okay. So I'm going to do this one a little fast. I'm sure you guys are fine with this. That's 1/2 y squared plus the natural log of the absolute value of y equals theta sine theta d theta. So the left side was just power rule. The right-hand side is another integration technique we should know. It's not u sub. Unfortunately, that doesn't work. Instead, it is integration by parts. So we let u equal to whatever variable that if we take its derivative, or whatever part of inside here, that if we take its derivative, it becomes simpler. That's how I like to think of it. So I let u equal theta, because if I take the derivative of u, I just get d theta. And then dv will be everything else, of course, with the differential, because we integrate both sides. This is, in its own way, a differential equation. And you end up getting v is minus cosine theta. Why did we do that? Well, integrating by parts, uv minus the integral of v du. Some people have other ways of doing it. That's completely fine. This is how I like to do it. Very methodical, I guess. So using that, we'll have minus theta cosine theta, uv, minus the integral of v, so I'll just make that a plus right now, cosine theta d theta, minus cosine theta. This is, of course, just plus sine theta, because that integral we do know how to do. Okay, so that's fantastic. Now we can plug this over. Oops. We can plug this in here. We get 1/2 y squared plus the natural log of y equals minus theta cosine theta plus sine theta plus some constant c. Technically, both sides will have a constant, but kind of like what I was talking about earlier, I'm just going to throw them all on one side. Now, this is a general, but we can get the particular solution because we know y evaluated at pi is just 1. Okay? So let's see, if I plug in 1 for y and pi for theta, I'm going to get 1/2 equals, well, that'll just be pi, because cosine of, you're going to get a -1 when you plug that in, so that makes that positive. And then, of course, sine of pi is 0. So c then is just 1/2 minus pi. We know what that constant is. So, of course, you could substitute that in. And now we have our particular solution. So nothing crazy there, not bad, just need to know to integrate by parts. Number 33 is the tank question. That's one that a lot of people struggle with. I think I've actually done this problem before. And essentially what we have is we have this saltwater mix, and we have 0.3 kilograms of salt water per liter that's running into a tank filled with 400 liters of water, which contains 2 kilograms of salt. And we have the rate that it enters, and we want to find the mass of the salt in the tank after 10 minutes. So the way that you do this, the way that I would recommend doing this, I'll scroll down here, is I start off with this. What is going in? What is our input? Well, the input is a 0.3 kilograms per liter, and we're going to go ahead and convert that to kilograms per minute. So we take the 10 liters per minute, right? That is right here. That's what it's entering at. So you're multiplying that by the 0.3 salt per liter. And of course, if you do that, that's quite simple. You're just going to get 3 kilograms per minute. Cool. So we have our input, 3 kilograms per minute. That's what we wanted. And we want to do the same thing with the output. Now, we don't actually know the output per se, but we know it's going to be some amount X per 400. I hate going back and forth between this, but that's just because it's initially filled with 400 liters of water. Okay? And again, we can multiply that by the 10 liters per minute to get the units we want, which is just X over 40 kilograms per minute. So that's the rate that it's going out. dx dt then, or you can call it whatever, I'm just going to call it x, is input minus output. So I'll spell it out. That's our rate. That's what we're looking for. That's our derivative. So in that case, it'll be 3 minus x over 40. Or, just writing it under one fraction, 120 minus x over 40. Okay, just a little algebra there. Okay, so 40 over 120 minus x dx equals dt. We've successfully separated our differential equation, and now we can just integrate both sides. Okay. So this will be minus, because of the negative on the x, 40, the natural log of the absolute value, 120 minus x, equals t plus some constant c. Okay. All right, so we can divide over and say that the natural log of 120 minus x equals minus t over 40. And again, yeah, it's that constant divided by negative 40. I'm just going to call it c. Raising everything to the power of taking the exponential of each side, you get 120 minus x equals e to the minus t over 40 plus e to the c, which I can also write as this. This is equivalent. Okay. All right, so we have that. And we know initially that the value is equal to, I believe it was 2. Let me double check. Yeah, 2 kilograms of salt. So that's at time equals 0. So that tells you that you have just 2 for that value. So 120 plus some constant c, we'll call it. That tells you c is equal to minus 118. Because if you plug in 0 for t, you're just going to have c, right? So then x equals 120 plus c, whatever that constant might be. So that's minus 118. Then x is, of course, 120 minus, just plugging in our constant, e to the minus t over 40. And they want to know after 10 minutes how much is there? Well, now that we have our general solution, it's quite easy. We just have to plug in 10. So if you plug in 10, that's minus 1/4, which yields 28.1 kilograms. Okay. So honestly, I think the only hard part about this is setting it up like this. If you can get that, it's not particularly difficult. Everything else was stuff we did, so not too bad. Last one is the Newton's cooling law. I did these because they also can come up again in the future, so I thought, oh, it'd be a good one to do. And Newton's law of cooling is one of them. So Newton's law of cooling is basically telling you that if you have some object and you leave it at room temperature, eventually it's going to reach that room temperature. And they give us a differential equation here. And they want us to solve the differential equation. And then given these initial values, what is the reading after 20 minutes? Okay. So they give us the differential equation, which is quite nice. This is 34, I think. So d capital T, temperature, by d little t, time, is K m minus T, or 1 over m minus T dt equals K dt. K is, of course, a constant as well. Okay, so integrating both sides, we'll have minus the natural log of m minus big T equals kt plus c, another constant. Or m minus t equals ce to the minus kt. Just raising everything, taking the exponential of each side, and e to the c is just a constant, so that can just go there. And then, of course, t then is m minus ce to the minus kt. So they give us the values in part B. So that is actually part A. We solve the differential equation. And we have a reading of 100 degrees Fahrenheit with a constant temperature of 7 degrees. And after 6 minutes, it reads 80 degrees. Okay. So we can really just plug in the values. It's quite straightforward. 100 degrees minus 70 degrees. And of course, e to the 0, that's your initial. Oops, that should be equal. That's just going to be minus c. And once you have that, well, you can solve for c, and c in that case, that c is just minus 30. And then in the other case, 80 degrees after 6 minutes, so 80 degrees equals 70 plus 30 e to the minus 6k. So all I did was I plugged in the values into here. Oops, use a different color. And now all you have to do is solve for k. K is our other constant, so we use the first initial value to solve for the constant associated with integration, and we're using the second initial value, well, it's not an initial value, but the second points to solve for this k constant, which is just a property of the equation that was given. Okay, so let's see. Subtract over, that's 10, so 10 over 30, so 1/3 equals e to the minus 6k. Or the natural log of 1/3, we want to solve for k, there's no need for absolute values, equals minus 6k. K equals minus the natural log of 1/3 over 6, which is about 0.18. And now that we have this value, we can plug everything into our temperature equation, right? And that is T equals 70 degrees plus 30 degrees e to the minus 20k. And we know what k is now. And if you plug all this in, you get about 70.8 degrees. Okay? So this one's actually quite straightforward. It's just a couple initial value problems, but it's all the same. So hopefully these questions helped. If they did, please like and subscribe. And I will be sure to do more of these problems. I think integration factor is next, so I'll try to talk about that in a couple days.